right, ladies and gentlemen, so we're going to talk about lesson 6.5, which is applying systems of equations. So we're going to take everything we've learned so far and we're going to start to put it all together for this lesson. Again, we're still working on that big skill of solving systems of linear equations approximately and exactly, focusing on pairs of linear equations in two variables. So there's no vocab today, but what we're going to do is I want you to create this chart in your notebook. We're going to talk about the three different methods that we've learned for solving systems of equations, and we're going to talk about when we use each method and how, so a brief summary. And this can be super useful as we move towards our assessment on this stuff, because you are allowed to use your notes on the assessment, and this chart can help you out. So the first thing we're going to talk about is when would we use graphing. So in that first box, we would use graphing when we have two equations in slope-intercept form, and we don't need to have an exact answer. An estimate of the solution is enough, or we have values that make sense to graph, where we have small integer values for a y-intercept, and we have slope values that are either a fraction of integers or numbers that would make sense. If we have really large or very, very small numbers, graphing doesn't make sense unless we're using a digital graphing tool. What I'm telling you as far as my class goes is that in general, graphing is not going to be the answer unless I specifically give you a graph to graph your equations on. However, substitution is going to be a way to go if we have them in both in slope-intercept form, which we'll talk about in a minute, or we have one variable isolated or easy to isolate in an equation. So that might be something like one equation's in slope-intercept form and one is in standard form, or we have x equals an expression and the other equation is in any form. Or if we have two in slope-intercept form. If I have two equations in slope-intercept form, and you don't need to write this in your notebook, but if I have y equals, 7x plus 3 and y equals 3x plus 7, I know that y is equal to both of these pieces, so I can plug it in and set them equal to each other. This is what we called special substitution in class and on one of the videos here. So special substitution is the way to go if you don't have graph paper and it's set up for two slope-intercept forms. All right, with that little side note there, the last method that we would use is elimination. And so we use elimination when both equations are already set up in standard form, and that means that our variables are lined up in columns. We have ax over ax, by over by equals a constant over a constant. Now, as we've talked about before, you can use any of these methods, and we're really going to focus on substitution and elimination. You can use substitution or elimination on any system. These are just leading you to the most direct way of solving. But if you know that you like to solve by substitution, you can always shuffle around your equation algebraically to isolate one variable and then follow the steps to solve. If you know that elimination is the way that works best for you, you can take any equation, shuffle them into standard form so you're ready to go for elimination. Up to you. This is just to give you a hint of which way is going to be faster to find your solution. Well, now let's talk about how. How do I solve by graphing? Well, the big idea here is that we want to graph both lines on the same coordinate grid and identify the intersection point or intersection points to determine the solution. If I have intersecting lines, I have one solution and I would name it the point where they cross each other. If I really have described the same line, they have infinitely many times that they touch each other, so I have infinitely many intersection points or solutions. If my lines are parallel, I know that I have no solution to the system. For substitution, the way that we would walk through the steps here is, and this is a summary, so it doesn't go into the details like we did on the other lessons, but the first step is you're going to substitute the isolated variable expression into the other equation and solve for one variable. Then you'll take the solution from that and plug it back into one of the original equations to find the other piece. Your final answer will be written as an ordered pair with x first and y second. Now, if you wind up at the end with something that looks like 3 equals 7, well, that's false. There's nothing you can do. So that would tell you that there's no solutions. If you wind up with a statement that's always true, like -2 equals -2, that tells you that there's infinitely many. So if you wind up with no letters left when you're isolating things, you have infinitely many or no solutions. Same idea applies with elimination. The steps for elimination, the big piece that's different in elimination is that you need to create opposite coefficients on one variable in each equation. And that's the idea of setting it up. So if you have 3y in one equation, you want a -3y in the other. If you have 2x in one equation, you want a -2x. You need to have something that eliminates when you add the equations together. Then you do your process of adding or subtracting the equations from each other to find one piece and take it back, plug it into the original equation to solve for the other piece. Same idea applies here though. If you wind up without any letters when you solve that elimination piece, there is no solution if it's a false statement, and there's infinitely many solutions if you wind up with a true statement. So in your notes, you should have a chart. And in your chart, you can summarize it. You can have words that are shorter than my words in the page here. You can take a look at the one on Teams for help. But I do want you to have this. This can be super useful as we're moving towards our assessment of this unit. So let's practice with this. First thing I see here is I need to identify the best method to use for the given system and then solve it. Well, if I look at my chart, I see that one variable is already isolated. So I know that substitution is going to be the best method here. If I substitute in, I will see that y equals this. So I take it and I plug it in where I see y in my other equation. So this turns into 4x minus 5 times my stuff for y equals negative 3. Well, my stuff for y is that 2x minus 3. Now I need to use some distributive property here. I know that minus 5 is really the same as plus and negative 5, so I'm going to remember where that negative sign is attached. I get 4x plus, well, negative 5 times a positive 2x is a negative 10x. Negative 5 and a negative 3 is a 15. Now I need to combine my like terms. 4x minus 10x is a negative 6x plus 15 equals negative 3. If I take away 15 from both sides, I get a negative 6x is a negative 18. So when I divide by negative 6, I find out that x is equal to 3. Well, now my next step tells me that I need to take that solution and plug it back into one of my equations to solve for the other piece. And in this case, I'm going to choose that first equation because it'll make my life easy. I could choose either one here. I have 2 times my stuff for x minus 3 equals y. Well, I'm going to plug in that x equals 3. So I get y equals 2 times 3, which is 6 minus 3. Y equals 3. My final answer here as an ordered pair is 3, 3. So there we go. Okay. Well, now let's make it one step more challenging. We're going to take a situation, and the first thing we'll need to do is to write those equations. Once I have my equations written, I'll identify the best method, solve it, and then interpret the solution. So Tamara can choose one of 2 plans at the gym. She can become a member for $80 and then pay $25 per month, or she can pay $45 each month without becoming a member. At what month will both plans be equal in cost? So the first thing I want to do is I want to write equations for the situation. What I see here is I see start value and a rate of change, which tells me that I'm looking at y equals mx plus b. So for my first one, I'm going to have y is going to be her cost, and x is going to be the number of months. So I have y equals her cost is equal to $80 plus $25 per month. For the other equation, her cost is going to be $45 times the number of months. There's no start fee here. So this is where that idea of special substitution comes to play. I see that I have y equals something and y equals something. I could graph it, but a slope of 25 makes really big slope triangles here. So I want to use this special substitution. I see that y equals this, so I'm going to plug it in where I see y in the other equation. And that turns into 80 plus 25x equals 45x. So I know that I can combine my like terms, so I'm going to take away 25x from both sides, and I get 80 equals 20x, divide by 20, and I find out that x equals 4. Well, now I'm going to plug it back in. I'm going to plug it into that second equation, so it's a one-step problem here. Y equals 45 times 4. So y equals 180. Now, last thing I need to do here is, this is a word problem, so I need to interpret the solution. What is the fact that x equals 4 and y equals 180? What does that tell me? Well, if I look at my situation here, this tells me that at 4 months, both plans are going to cost $180. So my final answer is that interpretation there, that I have 4 months, they both cost $180. So Tamara needs to evaluate, is she going to use it less than 4 months or more than 4 months to figure out which plan would be the most efficient for her wallet. Let's try one more practice problem here where we're going to write an equation to represent the system, identify the best method, solve, and interpret. So Paula and her sister are going shopping, and Paula buys 4 shirts and 3 pairs of shorts for $134. Her sister buys 2 shirts and 3 pairs of shorts for $100. How much does one shirt cost? How much does one pair of shorts cost? So with this one here, I'm going to be in standard form. I see a number of objects times their cost is going to give me a total price here. First thing I want to do though, because shirts and shorts are both S's and I would get confused with my variables here. So I'm going to use X and Y, but I'm going to say that X is going to be the cost of a shirt. There we go, cost of shirt. And I'm going to put Y is my cost of shorts. I could do it the other way around. It doesn't really matter which one's first, but I see that in my situation, I listed shirts first. So I'm just going to write it out like this so I have an idea of what I'm working with. For Paula, I see that she bought 4 times the cost of a shirt, which is X, plus 3 times the cost of shorts, which is Y, had a total price of $134. Her sister bought 2 times the cost of a shirt, plus 3 times the cost of shorts, for $100. Now that my situation is written out, I need to figure out how I can eliminate one of my variables. I see that they're all positive coefficients, so nothing's going to eliminate directly, but I see 3y and 3y. So I know that if I set this up as a giant subtraction equation, I will have the y's eliminated. And like we talked about in the other video, you can do it this way, or you can multiply it out by a -1, or you can get the x's eliminated. Whatever you choose to do to get something to eliminate, you'll wind up with the same answer. What I see here is I have 4x minus 2x, so that gives me a 2x. 3y minus 3y goes away. 134 minus 100 is 34. So I have x. When I divide by 2, I find out that x equals 17. If I go back and plug it in, and I'll plug it into the second one here. I think I have it the other way around in the notes, but that's okay. I'll get the same answer. If I plug it back into the original equation, I have 2 times my x value plus 3y equals 100. Well, my x value was 17. So 2 times 17 is 34, plus 3y equals 100. If I subtract 34 from both sides, I get 3y equals 66. So I find out that y is 22. Now to interpret here, I need to go back to my original idea. I know that x is 17 and y is 22. So I'm going to go back to my original work here. The cost of a shirt is going to be $17. I need to make sure I have a label on it because it's a word problem. And the cost of shorts is going to be $22. Got both pieces labeled appropriately for my final answer. So now it's your turn to practice. The homework assignment is page 367, numbers 9, 10, 11, 14, and 15, and then 27 through 30 and 34. When you're doing this homework assignment, you can expect that these ones here, 9, 10, 11, 14, 15, and 34 look like the practice problems we did. Those are the write out the situation, identify the variables if necessary, and then solve for a final answer. The ones in the middle there are those multiple choice practice, those test prep practice ones, and those are kind of tricky. So some of them ask you to reach back in your brain to skills you haven't worked on in a while. Do your best. The key will be posted, get the assignment submitted after you self-grade it, and then we'll have one more new lesson before we finish up with chapter 6 here. Thanks, guys.